Alright guys, now we're going to look at how to take these motion maps and how to get more information from them by making them into position time and velocity time graphs. Now motion maps are 1D representations of motion, meaning that they are all left or right. You can go up and down if it's stationary, but it really isn't two-dimensional. But we can create 2D position time graphs from a motion map. So this top motion map is the one that we're going to be using. What you have to do is label your axes on your graph. So position versus time. Time is on the x-axis. So I'm going to count 1, 2, 3, 4, 5 seconds. And then position is on the y-axis. 1, 2, 3, 4, 5 meters. And at time is 0, up here, this is when the gun just first goes off for a race. At time is 0, you are at 0 meters. At time is 1 second, you are at 2 meters. So at 1 second, we're going up to the 2 meter line. Time is at 3 seconds, you are at 4 meters. Okay, and then you can connect these dots with a line of best fit, because this can tell us the general trend over time, and we can make predictions of where the object is either at a time we did not take data for, so like at half a second, or for a time that we haven't yet reached, like 3 seconds. Or 4 seconds, okay? So we're going to do it one more time. Across the x-axis, we want to put 0, 1, 2, 3, 4, 5 seconds. The y-axis, 1, 2, 3, 4, 5 meters. At time is 0, we are actually at 0 meters. Time is 1, we are at 3 meters. Time is 2, we are at 5 meters, and time is 3, we are at 6 meters. So here, this line of best fit is actually going to be slightly curved because we have a curved relationship in that graph. So now here's an example problem. Robin was observed while roller skating down a marked sidewalk. The table to the right shows the position at different times. So plot the position time graph. So we need to go up to 30 meters in 10 seconds. So every line at the bottom, I'm going to go up by 2. So 2, 4, 6, 8, 10 seconds. And every line up the top, I'm going to go up by 5. So 5 meters, 10 meters, 15, 20, 25, and 30. Okay, so at time is 0, we are at 10 meters. So time is 0, 10 meters. Time is 1 second. Is at the halfway point, we're at 12 meters. Time is 2 seconds, is at this first line, we are at 14 meters. Now time is 5 seconds, we counted by 2, so 2, 4, 5 is about halfway through here. We're going to be all the way up at 20 meters. Time is at 8 seconds, 2, 4, 6, 8. We are at 26 meters. And time is at 10 seconds, we are at 30 meters. So if we draw a line of best fit, I'm going to do this in a different color. That is pretty much, let's pretend that didn't happen, a straight line. So we plotted our position time graph. Now how far away from the starting point was he at 6 seconds? So at 6 seconds, 2, 4, 6, we were about at 23 meters. But we started at 10 meters. So 23 minus 10 is 13 meters away. Was his speed constant over the entire trip? We can do this by actually calculating the slope of that line. So since it is a straight line, we can say yes, but we can also calculate what his speed was. So we went from 0:10 to 10:30. So rise over run is change in y over change in x. He ended at 30 and started at 10. He ended at 10 seconds and started at 0 seconds. So this is 20 over 10, which is 2 meters per second. Looking at this following position time graph, I don't want you to calculate anything, I just want you to read the graph and let me know. So do the cyclists start at the same point? Yes or no? So we have 2 lines. Cyclist A starts here and travels all the way up. Cyclist B starts here. So in this scenario, cyclist B actually has a head start. At 7 seconds, which cyclist is ahead? So here's 5 seconds, they're at the same location. At 7 seconds, let's say about here, cyclist A is actually farther ahead because his distance, if we were to say this is 7 seconds, and we follow them both back to this line, cyclist A distance is further, okay? Which cyclist is traveling faster? Now remember, speed is the slope of the position time graph. So through this entire trip, cyclist A has a larger or steeper slope. So he is traveling faster at the 3-second time. Are their velocities ever equal? No, because the slopes of their line are never equal. And what happens when line A intersects line B? At this location, right at the 5-second mark, that's where they are in the same spot at the same time. They travel the same distance and they are passing the same marker at the same time. But one person is still traveling faster than the other, so A travels on forward at a faster rate. Next up, we're going to look at velocity time graphs. Okay, velocity time graphs are slightly different than position time graphs because instead of just having one quadrant, they actually use quadrants 1 and 4. So we can create a velocity time graph using our position time graph. If our first position time graph looks like this, the slope of this line is a constant value and it is positive. So this horizontal axis would be if our velocity was 0. Since this is constant and positive, we would actually draw a horizontal line in the positive sector. Now if it had a slope of positive 3, we draw that horizontal line at 3. If it had a slope of positive 7, we draw that horizontal line at positive 7. Okay, down here, this is actually our acceleration time graph, which we are not getting to quite yet. Okay, so we looked at motion maps, we looked at position time graphs, and we looked at velocity time graphs relatively quickly. When we meet in class, we are going to go over these a little bit more in depth, and we're going to practice not only graphing and plotting these graphs, but also interpreting these graphs. See you guys soon.